Before digging into the details of how to design and build a video controller, a hardware video controller, I want to talk briefly about what a stream interface is and why would we need it. So by now you should be familiar with what random access is because you have dealt with processors, you have probably used microcontrollers, and you have dealt or accessed data in different I/O cores, or actually maybe its main memory in its RAM, and you access it randomly. And what random access tells me is you can access any of the cores or any location, no matter where it is physically, at the same exact time. So you can actually access the internal register for this particular core at the same exact time for accessing this particular core. And it doesn't matter where the core is actually located. And the way you do this particular data transfer between a processor and a certain location in memory or an actual I/O, it's just you specify the address on the address line, you tell it what type of transaction, whether it's read or write on the control lines, and then the transaction happens on the data line, whether it's a read or write. When we're dealing with video, it's a little bit different. The data transfer is not in the same. It's not this sporadic, okay? It's actually continuous, and it has to be continuous because you keep providing the monitor a stream of pixels all the time so that it actually displays it in a very smooth pattern. And the way you do it is using what we call a stream interface. So the data is streaming all the time, continuously. Okay, so a stream interface provides a high speed and it's a unidirectional data link between fixed points. What do I mean by that? Well, what you will see is actually you'll have one source of data for the pixels, and that source basically will generate these pixels data over and over at a very, very specific steady rate. And then you're going to have something what we call a sink, or something that consumes that particular generated data. Okay, so we have a source and a sink, and we're going to connect them together, and so forth. And that particular one, the sink here, becomes a source for maybe another sink or whatnot. So we have some sort of fixed points over and over again. What I want you to know is the following, that a pixel actually goes from here, it passes through here, and then it gets processed in here, maybe added, modified, done something to it, and then goes in here. And this happens over and over and over again towards the end here. Then you connect it to the VGA monitor or VGA screen, or actually just the VGA port, and maybe your monitor is not based on VGA, but it can actually have some sort of a transformation. But the bottom line is actually you're streaming it. So one thing to think to point in here is actually I didn't have to specify an address for the points. I didn't have to tell it whether it's a read or write. So no control lines were needed, and the transfer is always one directional from one source to a sink to another source from then to another sink to another sink then to another sink. So it is not random access. It is stream interface. And the reason why I'm introducing it in here and I'm talking about it is because this is what we will be using to build the video controller. And if you have several things that you need to do with the pixels, you need to actually use streaming interfaces. Streaming interfaces are not restricted to video systems. So you will also see them in audio processing and communication links, especially with cryptography, maybe high-speed serial links. You're going to see it over and over in many other systems. So let's talk a little bit more about these stream interfaces and how we control the flow of the stream interfaces. And as it turns out, that there are multiple ways you can connect sources and sinks. And again, remember, a source generates pixels, a sink actually consumes these pixels, and that sink might then becomes a source for another sink, and so forth. So in this slide in here, I'm showing you 3 different ways that we can actually utilize or connect, or how the pixels flow through the different sources and sinks using a stream interface. So the first one, which is the easiest, which we'll be starting with, is actually the centralized flow control. What the centralized flow control tells me is you have a source, it generates pixels, and then it just sends it. It doesn't care what's happening next, it just sends it all the time. In this particular case, actually, that pixel goes to the sink in here, and that sink does process or do whatever it is, and it has to process it, and then it sends it to another sink, and so forth. And at the very end, you have like some sort of a pixel data you can send to the monitor. So we call it centralized because generally speaking, you will have some sort of an agent or an entity in here that regulates this flow, or actually talks to all of those 3 sinks or sources or whatnot, and it just regulates that type of flow. So there's another one that is a little bit more complicated but more robust, and this basically is what we call a distributed flow. So instead of having the entity that is centralized that is controlling everything, it's actually distributed. The control is distributed, so each one of these particular sources or sink will have a couple of signals, or actually will have an output that tells me that the data is valid, and the sink in here will tell me I'm ready to do it. So what we have in here is some sort of a handshaking mechanism. So this tells it, hey, I have some valid data, and I'm gonna only be able to send it to you when this one here tells me, yes, I'm ready to do that. So in this particular case, I can have something we call a back pressure. So if one of the sinks in here is actually busy doing something, it actually can perform some sort of a back pressure to stop the source. And that's what we call a distributed flow control with back pressure. So now, if we have, let's assume that we have different sources and sinks and they operate at different frequencies, we can actually solve this by inserting some buffers in the middle between them. So we have now what we call distributed flow, but this time with FIFO buffers. So the sink in here does not need to basically slow down the source at all, because what that happens is the source will just basically push its data to the FIFO, and you have the same handshaking mechanism and so forth. I'll spend a little bit more time on this one here because it's important, and we're going to utilize it later because it actually leads to a very robust controller later on. And the reason why we might want to use this is the following. So we have talked about that we have a source in here and we have another sink in here, okay? So what we have is a source, and that source might be operational at a very high speed. And let's, for the sake of example, let's assume that this is actually operating at the 40 megahertz, and the sink in here operates at 10 megahertz. So the way that you can actually tell these two or let these two communicate with each other is by slowing the source itself. So you're going to have to tell the source, yes, you're operating at 40 megahertz, but I'm not going to let you send me data at 4 megahertz. What I'm going to do is I'm going to let you send me one packet or one pixel every 4 cycles. And that's basically because it's because the sink is actually 1/4 of that. And that's what you see in here. So what you see in here is like we're going to send a pixel and another pixel, another pixel, another pixel. And the very end in here, what I want you to see is I have 1, 2, 3, 4, 1, 2, 3, 4. So I basically have 8 packets or 8 pixels that were sent. However, some of the sources, yes, it might be okay to slow them down and whatnot, but some sources actually have a lot of overhead with reading. So for example, if you're reading from memory, let's assume SD-RAM, as it turns out, it has some sort of an overhead to just access the memory. Once you access it, you can just read very, very quickly in a burst mode or write very, very quickly. We care about read for now because we're just reading pixels. So let's assume pixel information in here are stored in some sort of a memory, and I want to read maybe 1,000 pixels at a time, 1,000 pixels at a time, or something like that. So what we can do is we can insert that FIFO buffer, and this is where it becomes very helpful. And we're going to say, okay, I know that overhead to access the information inside this particular source is really expensive, so I'm just going to access it once. I'll read it at the 40 megahertz, and then I'm going to store it in the FIFO, and then the sink will just basically read it very slowly. And this is what you see in here. So in here, what you see is I basically pushed 4 pixels into the FIFO, and then the sink actually read it very, very slowly. And basically what I'm saying in here is you can just basically read it at the 40 megahertz, and the FIFO will allow you to read its information slowly at 10 megahertz. At the end of the day, both system in here have like, this is 1, 2, 3, 4, 1, 2, 3, 4, basically have 8 packets or 8 pixels that were sent. But the FIFO just allowed me to employ something a little bit more robust than just basically back pressure in stopping or slowing down my system just because my sink or doesn't or is unable to process the data as fast as I want it to.